what we mean when we say the probability. So let's say the probability of event A. So it could be the probability that you throw a coin in the air and it's a head, or the probability that it rains tomorrow. Event A is just a placeholder for you throw the coin and it's an A, or tomorrow's weather, or whatever. And we tend to abbreviate it as P of A, or in some books as prob of A. So if you ever see capital P of A or prob of A, they just mean the probability of event A. Right? Now, formal definition, well, sort of semi-formal, it's the proportion of times you expect event A to happen. Now, I'm using the word proportion as just a catch-all. Probability, the number, right? How many times out of 100 times, or what fraction of the time, any phrase like that, I'm calling it a proportion, right? Can be a decimal, it can be a fraction, and it can also be written as a percentage. So let's take the simplest example of a probability I can think of. Let's suppose I throw a normal coin in the air, nothing special, and it lands down. What's the probability that it's going to be a head? Well, it's the number of times a head can happen. Very trivial question, because there's not a lot of this. And it's divided by the number of times anything could happen. So it would be 1 out of 2, wouldn't it? There's one head and there's 2 things that could happen, right? Heads or tails. We'll forget about landing on its side. That is the probability of a head. Or isn't 0.5 the same thing as a half? So you could say the probability of getting a head is 0.5. Or couldn't you call it 50%? So it really just depends on what the WebAssign says. If WebAssign says I want a fraction, do that. If it says I want a proportion, do that. If it says I want a percentage, do that, right? So, you know, sometimes it's fussy. If you do this when it wanted that, it's going to say you're wrong. Well, technically you're right, but not in the form. So when they say fraction, when they say proportion, but they're more likely to say decimal. And when they say percent, right? Let's look at a slightly more complicated, but only slightly. Suppose I've got a normal, good old-fashioned dice, nothing special. What's the probability that I get a 3? Well, there's 1 3 on a normal dice out of 6, so there's my answer, 1/6. And I could turn that into a decimal or a percent. It's quite ugly when you write it that way, so I'll leave it as a 6th. But you can also do events that are a little bit more than that. For instance, what's the probability that I get an even number when I throw the dice? Well, there are 6 things that can happen when you throw a dice, agreed? But how many of those 6 are even numbers? Agreed. And a general rule, I call it style points, things that are fractions shouldn't be simplified down if possible. So if it is 3/6, remember to call it a half, right? That's just good math. Or 0.5 or 50%. So the probability is basically the proportion of times you would expect that event to happen, right? Now let's look at some of the properties of the value of a probability, any probability at all, actually. Would it make sense that probability has to be a number between 0 and 1? You couldn't have a probability of, I don't know, 11 thirds, right? You would never be able to get 11 ways of it happening, but there are only 3 things that could happen. And you've somehow managed to figure out 11 ways to make that happen, right? It's just back to front, right? It's not going to happen. Any event that has a probability of 0 is technically never going to happen. At the other extreme, any event that has a probability of 1 is guaranteed it will happen. And right in the middle, I'll put, since we're doing the decimal version right now, I'll put 0.5. We even have some terms in the English language which we use for something that has a probability of a half. Don't we say things like, it's just as likely to happen as not happen? That would be an example of a 0.5 probability. It's got an even chance of happening. Ever heard of that phrase? Somebody might use it. That's just another phrase for that. Isn't that kind of, yeah, it's likely harm, or it might not harm. It's about the same, right? Now, as you go this way, isn't it more likely to harm? So a 0.6 is more likely to happen than something has a 0.5 event, right? Something whose probability is 0.99. Isn't that almost always going to happen? But now and again it would, right? Now, if you go the other direction, of course, it makes sense then that these are things that are less likely. So if you had a probability of an event being 0.4, wouldn't that be less likely to happen than a 0.5? But wouldn't a 0.0001 almost never happen? But occasionally it does, right? So you've got this probability kind of spectrum from 0 to 1. Of course, if you do it as percentages, 0% or 100%, would you agree they're just the same idea, but written in a different kind of unit, right? Percentage unit instead. Me personally, it's just my personal preference. I like percentages when you talk about probability. It makes it, for me, it makes it easier to compare two events. If I said event A had an 80% probability of happening and event B had a 17.5% chance of happening, I kind of know which one's going to happen more often than the other. And I even get a feeling for how likely or unlikely they are. But if you say one of them's 17/83 and the other's 15/42, isn't it very hard to figure out how big they are and who's biggest? Right? Just fractions don't really lend themselves very well to comparisons. Decimals are okay. You know, I think I could compare decimals pretty well. So far, so good. Right. So let's introduce you to some more guys. There is an event called A with a little c. You read it out loud as the complement of event A. So it's the other event, right? If you think of, there's two things that could happen. The event A happens or it doesn't happen. Can you think of the complement of A being A doesn't happen? So let's give you some examples of that. Suppose A was throwing a dice and getting an even number. Then wouldn't the complement of A be getting an odd number? Does that make sense? The complement is the opposite event. What do you call it when the A doesn't happen, essentially? Suppose I told you that A was that you got a tail when you threw a coin. Then what would the complement of A be?
Getting heads.
Getting a head. Let's be sneakier. Suppose I said A was that you took a card and you found the probability you got a club. So A is you pick a card from a deck of cards, no jokers, right? Just normal cards, right? And you get a club. What would the complement be?
Getting one of the three other. I
Yeah.
don't remember the words for that.
Yeah. Should we just call them not getting a club then?
Suits. One of
Yeah,
three suits.
getting one right. There are actually, we do quite a lot of questions with cards. So after I've done this, I'll talk a little bit about cards then. They're hearts, in no particular order, diamonds, clubs, and spades. So the complement of A would be that it was one of these cards that you got, right? Now, there is a very simple formula that connects these two probabilities. The probability that you get a club, or whatever it might be, A, added to the probability that you get the complement is always 1. Does that kind of make sense? Heads, tails. If one of them is a quarter, won't the other be 3/4 then? So if I told you, for instance, that the probability of A was 0.3, you should be able to, even although you don't know what the event A was, but you know what its probability of happening is, shouldn't you be able to tell who this guy is? Like, what would be the proportion, the decimal for the complement of A in this story?
0.7.
0.7.
Okay. Did you do something in your head like take 0.3 away from 1, or a calculation similar to that? That's how you would get the 0.7, isn't it? Now, I could rearrange that formula. Couldn't I say the probability of A is 1 take away its complement? The probability of a complement is 1 take away A, probability A, or I could write it like that. So I'm just writing it that way, but couldn't you use it in 2 other ways? So far, so good. Now, moving on, still on these probability intro stuff. There's a thing called the sample space that we deal with in probabilities. The sample space is basically, SS for short, a list of every possible event. Now, some sample spaces are tiny. So let's give you some of the baby ones before we start looking at the difficult ones. For instance, if you do a coin in the air story, the sample space will be heads or tails, right? If you do a dice, won't the sample space be you get a 1, a 2, a 3, a 4, a 5, or a 6, right? And I'm not doing cards, but I'll write it down. If you did cards, wouldn't you get an ace of hearts, a king of hearts, a queen of hearts, and does anybody know what how many cards there are in a normal deck of cards?
52.
52. Okay, so I'm going to, at this point, it's probably a good idea to talk about just cards, because there's a lot of probability questions that use cards, right? They're a good example of situations where you might want to do things. So here are what a set of 52 cards looks like. They go in 4 suits in no particular order: clubs, spades, diamonds, and hearts. This club, on to that, clubs. The clubs and the spades are black cards. I mean, if you had a deck of cards and you looked at them, they're black, right? And diamonds and hearts are red cards. The reason why that's important is you might get a question like, what's the probability you get a red ace, right, for example, right? Then you'd have to realize that there were 2 red aces in the deck. Now, every deck of cards has 13 in each of its suits. These are called single suits. And I will do them this way. Ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, Queen, King. And can you trust me, the same thing happens in the others. So I don't need to write them down. These three guys at the end, the Jack, the Queen, and the King, these are called face cards. I think they get their name because in most decks of cards, aren't they Jack, Queen, and King? Aren't they somebody's face, a person's face? Jack, Queen, King. They're the only ones that have faces. These guys here have numbers, and that guy up there is a special case. On the deck of cards, it just has a big A in it, or just a single club symbol, perhaps, but most likely an A. Are we cool with the deck of cards, right? So I'm going to use a deck of cards because I can ask more interesting, complicated questions. The sample space is all 52 of these cards, right? That's if you take one card out of a deck, is it there? One of those 52 things is going to have, right? One of those cards. So if I asked you to find what's the probability that it was a red face card, you would say 52 goes in the bottom because whatever is in the sample space always goes in the bottom, right? That's how many ways things can happen. And red face cards, well, wouldn't there be diamond face cards and heart face cards? And in diamonds, aren't they Jack, Queen, King? And in hearts, isn't there Jack, Queen, King? So that ends up being 6 cards altogether. Are we comfortable with that? Can this particular fraction be simplified? Can you simplify 6 on the top out of 52?
Yes.
Okay, what does it, you're correct. What does it become?
1 second. It becomes 3/26.
Good. Let's show you what you could do, especially when the fractions get really, really big. It's very hard to see what they simplify down to quickly. So I've got too many windows open here, so I don't know where the heck I am. Yeah, you're looking at my screen now. Okay, so you can go 6 divided by 52 and you get the horrible decimal. Then you hit the math button, choice number 1. And what that does is it takes your answer and makes it a fraction. And 326. So it's not difficult, right? I mean, just make sure that you plug your top number divided by your bottom, and then, hit the math button and simplify it if necessary. What about this kind of back to front one? What's the probability that it's not a king? Whenever you see the word not, it's a compliment, right? Not a king. How many of those 52 cards are not a king?
48.
Okay. Wasn't it easier just to find out the kings and take it away from 52? Although you might not have thought it, we were using that property earlier, right? You know the complement, you know the original, right? Sometimes it's less work to find the opposite of what you want to get the thing that you do want. So in this case, we have that. And this one actually, I believe, simplifies down to 12/13. Any questions so far? Are we good? Right, let's give you a couple of card questions. I'll keep these here for you. What's the probability that you get an ace? For the second one, what's the probability you get an ace or a king? It's an interesting way of phrasing it. And the third one is, what's the probability that you get a red ace? Right. Try and find those 3 probabilities. You got a minute to do it. Gives me a few moments to load up our questions as well. Okay, any volunteers? I'm picking the bottom number. Isn't the bottom number 52 cards? So we don't need to worry about that right now. Okay.
Well,
Okay, what's the probability that you pick an ace from a deck of cards?
1 in 13.
Correct. Ace or a king?
Out of 13.
Say that number again.
2 out of 13.
Agreed. Isn't there 4 aces and 4 kings? So that adds up to 8. And you're quite right about 2 out of 13. What about a red ace?
1 in 26.
Agreed. Do we feel, as long as we keep the probability simple, isn't it just a matter of counting correctly? You know the bottom number's 52. Just make sure that you've got them. You might even want to get a deck of cards just to get comfortable with them, and you can actually take them out and count them if you get stuck. So far, so good. Let's move on, still on sample space. Start a new page. So suppose we have 6 people in a class, very small class, and we're going to just give them the names A, B, C, D, E, and F. That way I don't have to keep writing Janice and John and whatever, right? A, B, C, D, E, and F. If you pick one person, so I'm going to pick one of you to get a $10 bill because I'm generous and I'm picking one of my students at random to get a $10 bill. Since it's one person, won't the sample space consist of 6 separate things, right? And what's the probability that A gets picked to get the $10 bill? Well, there's only one of him or her out of 6. There's your probability. Now, this time, we're going to pick 2 people. And I'm going to give both of them, right, $10 bill. Now, the sample space gets a little bit messier now. Couldn't I pick A and B? Right, that could be the 2 people I chose. I could have chosen A and C, A and D, A and E, and A and F. They are all possible things that could happen. They're in my sample space. Why don't I write down B and A as well? Why would that not be necessary? I've already got A and B. Why do I not bother doing B and A?
Because it represents the same value.
Yeah, it's the same people, isn't it? There's no significance to the order. Now, the problem that we've got here is sometimes the sample space is not as easy to write down as you might think. Why didn't I, for instance, do A and A?
Because it's one person, not 2.
Yeah, I can't say I'm picking Janice twice, right? I'm picking 2 different people, right? That would be implied. Now, that means that my next law is going to be BC, BD, BE, and BF. Wouldn't those represent different groups of 2 people, right? No duplicates yet. What do you think I'm going to start my next column with? Because you have to have a nice systematic way of doing these. If you just write them as they come into your head, you'll get most of them pretty quickly. But when you get stuck on the last 2, because you can't quite think of who you've missed. Right, in this organized way, that's not going to happen. Who do you think I'm going to start the next one with then?
C.
Okay, and C with what?
C with G, C with E, and C with F.
Do you see that there's a kind of method to my madness here, isn't there? Isn't there a kind of systematic way? So the next one would go D and E, right? And D and F. And then the last one would be E and F. Do you see that now we have got all the possible ways that 2 people could be chosen? And the total number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's check that. It's 15. So when I do my probability, isn't it going to be 15 on the bottom? So let's look at some probabilities then. What's the probability that I pick A and somebody else? But A is one of the people I picked, right? Now, when it was only one choice, right, one person getting picked, the chances that A got the $10 bill is 1/6. Do you think they've got a better chance now, the same chance, or a worse chance than here?
Better chance.
Okay, and let's find out how much better. Isn't there 1, 2, 3, 4, 5 of these where A got chosen to get the money? So 5, oh, in fact, hasn't their chances of getting the money now doubled? Right, 1/6 is now 2 people, 1/3. So far, so good. Now, I'm not going to do a 3-person pick, because you imagine that would take a long time, because there's lots of different ways of picking 3 people. Actually, maybe not as many as you think, but there are a fair number. There are 15 of them altogether. And then 4 people, which actually isn't that many. And lastly, if I picked all 5 people, let's do it as a silly one. If you pick 5 people and you're going to give all of them a $10 bill, won't the sample space consist of A, B, C? Oh, I should change my rules there, 3. I meant 6 people. Won't my sample space consist of just one thing? Everybody. And so what's the chance that E gets picked? 1 out of 1, guaranteed. What about F? Still 1 out of 1. Can you, it's a very silly kind of probability, but you know, it works, right? It works for every situation, as long as you can create this sample space. Now, when it's one pick, I don't think you really need to write the sample space. Couldn't you do it in your head? Would you agree when it goes to 2 people, it was worthwhile? Because if I went and said to you, you're picking 2 people, what's your chances that A gets the money? Wouldn't it be quite hard to know that the bottom number was 15? And it might not be obvious even what the top number is. So you need to create sample spaces when the questions start getting a bit more complicated. Next fella is going to be called mutually exclusive events. And the other one is called not mutually exclusive events. So, definition. 2 events, A and B, are said to be, I'm just going to call them mutually exclusive, right? So I don't have to write the word again. So 2 events, A and B, are said to be mutually exclusive if they do not have, any common events. And I guess I should put in the word shared common events. So if A and B don't have anything that they share, right? There's nothing in A and nothing in B, right? They're called mutually exclusive. Let's do the card one. If A is the probability or the event that you pick a card and you get a club, and B is you pick a card and you get a diamond, those 2 events are mutually exclusive. Would you agree that if you're a club, you can't be a diamond, and if you're a diamond, you can't be a club? Those share no events in common, right? Ace, king, queen, they're all different events. So these 2 are mutually exclusive. Suppose A was you got a club, and B, you got an ace. So here are my 2 events. And these are not mutually exclusive. Why is getting a club and getting an ace, why are they not mutually exclusive?
Because clubs have aces.
Right, isn't there at least one card, the ace of clubs in this case? And it only needs to be one that they share. An ace of clubs is an ace, but it's also a club. That's what makes them not mutually exclusive. So why is that a definition that we even need to get concerned with? Well, because of this. If two events, A and B, are mutually exclusive, then the probability that you get an A or B is the same as finding the two probabilities separately and adding. And we are using this word or. The word or, and later on there's another one called and, gets used in probability. And the word or has a very specific meaning, right? It means A or B. A or B or both, right? You could either have one, the other, or both. That is what I think is called in English an inclusive or. You know, there's another kind version of or, which is the exclusive or. Right. Give you an example. Suppose you get a kid. You could say to the kid, you can have ice cream or cake. Right. And in your world, ice cream or cake would mean you can have ice cream or you can have cake, but you're not allowed to have both, right? But in this world, you are allowed to have both. In other words, both things added together. So what's the probability? Let's pick. What's the probability you get an ace or a king? Would you agree aces and kings are mutually exclusive? That means you can find the probability of getting an ace and adding it to probability that you get a king, which is basically just 4 out of 52 in both cases. And that becomes 8 out of 52. Now, wouldn't most of you just add those together anyway, because it's quicker, and just say 4 of these plus 4 of them is 8? Are we good? Now, suppose they're not mutually exclusive. That causes problems. So let's suppose we have A is aces and B is red cards. If you want to find the probability that you get an ace or a red card, right, that's an A or a B. Don't do this because it's wrong. There are 4 aces. There are altogether 26 red cards, and the bottom number is 52. The bottom number is 52. I call this double dipping. Aren't aces and red not mutually exclusive? Aren't there some cards out there that are both red and aces? How many of them are both red and aces? How many red aces are there? 2. So if you wanted to get the correct answer, wouldn't it be 4 add 26, take away the 2 that you've already counted? Do you see how you have to compensate with that -2 to get the right probability? And so the correct answer would be 28 out of 52, which I believe is 7/13. Now, if the 2 events had nothing to do with each other, do you see you could just add them together? Couldn't you just say 4 add 4 out of 52 and get 8 out of 52, which is what, 2 out of 13? So be aware that things could be mutually exclusive, in which case just add them. But if they're not mutually exclusive, don't you have to take away the double dipping? Right, let's do another double dip one. What's the probability that you get a face card or a heart? Okay. face cards. Where's my little list? Here we go. I lost my little list. Here we are. Here's my little list. Isn't there 3, 6, 9, 12 face cards? Great. 3, 6, 9, 12 face cards. Plus, how many hearts are there?
13 less the 3 that you've already counted.
And then, just as Rob said there, isn't there 3 cards that are red? Sorry, 3 cards that are face cards that are hearts. Right, so the double dipping thing. And so you put that together, you get 22 out of 52, which is 11 out of 26. So the counting's getting a little bit trickier now, isn't it? And mutually exclusive is our way of making sure that you keep it honest, right? That you don't count the same thing twice, right? The double dipping, as I would say. Are we cool with that? Okay, things are good. Let me show you a different word. That's or. When you get in probability, an ace and a heart, which is not really the way you would probably want to phrase it in English. I want you to realize that what we're saying here is the ace of hearts. It's basically when you see the word and, think of it as meaning both. What's the probability you get a card that's both an ace and a heart, right? In that case, there's not many, isn't there? Only one ace of hearts in a deck. So that would be a 1 out of 52. But suppose I said, what's the probability that you get a face card, right? And it's red. So what you're trying to count here is essentially red face cards, isn't it? Things that are both red and face cards. So red face cards, how many of those are there? How many face cards are red?
24? No.
There are
No.
6. There are 6
Right.
face cards that are red.
There's 3, whoops here, 3 red ones here, 3 red ones here. There are 6. And I believe you can do that with a 2. So that's 3 over 28 when you simplify. What's the probability then that you get a heart and a king? What number belongs in the top? Heart and a king.
1.
What's the probability that you get red and a king?
2.
2 and 52.
Right? Oops. 28, right? Are we comfortable about the and thing and how that's essentially a different situation from the or thing? Aren't the or things you add things together, and the and you try and find what's how many events are both things, right, at the same time? Now, if I go back to this guy, if you want to write it down as a formula, there is a formula that says the probability of A or B. And it's the probability of A, add the probability of B. And when you say take away what I call take away the double dip, it's take away the A and B. So if you ever see a formula that looks like that, it's basically saying how many face cards, how many hearts, take away both. Isn't the double dipping the both? And the both are called A and B. Although in some textbooks they put in the word both and they say both A and B, which is probably a better way of phrasing it. Any questions? Because we're pretty much finished for today.